Hello everyone, my name is Ever Barbero, and today I want to talk about Mohr Circle 3D. This is in chapter 3 for MAE 343 Intermediate Mechanics. So first a review of Mohr Circle 2D, and I have to say that I strongly recommend you go back and watch the video for Mohr Circle 2D. If nothing else, because that video explains something that is not explained in the book, and that the main reason for Mohr Circle 2D is to be able to find components of stress in any orientation, not just the principal values. But anyway, it's up to you. A review that video would be better before watching this video. But I will review a little bit so that we can go forward. All right, so then here what we have is a sketch from the previous video, and which is pretty busy, and it shows the original stress element with the stresses applied 80, 0, and minus 50. And then it shows the stress element for the principal values of stress, sigma 1 and sigma 2 Roman in red, which are in the diagram, they are here, sigma 1 and sigma 2. And the way I try to convince everybody to do Mohr Circle is graphically, because then you don't have to remember any equations. And to do it graphically, basically what we get is first we find the center point, which is sigma x plus sigma y divided by 2, 80 plus 0 divided by 2 is 40, that's the center of the circle. Then find the radius. For that we need a number, which is this distance here, which is very easy because it's 80 minus 0, sigma x minus sigma y divided by 2. A square plus tau square and give us 64. And if you take this r and then now you go here where you want to go to find this value, well, that's also r. And then you add 40 plus that r, and it gives you 104 for sigma 1. And sigma 2 is sigma minus r, which is minus 24, and is there. The angle therapy is negative because the angle is always measured from the original point A, this point A, which in the diagram is there. And you gotta go from there to here. So the rotation of the stress element, this stress element, which I cannot draw on top here, so I draw here. This stress element has to be rotated, how much? This angle, which here is doubled, all right? But these angles, with this arrow like this, the value will be negative because the positive angles are counterclockwise. So you calculate using tangent, and you have the 50 and the 40. Then you have to put a negative sign because you can see there that the angle is negative. And then, of course, if you want the tau max, then you know what the tau max is, r, and where is it located? It's here at the bottom of the diagram. This value also is okay because you will see later in chapter 5 that the sign of the shear is irrelevant for failure. So the material doesn't care whether you put plus tau max or minus tau max, it will fail the same. And this is true for all materials. So, okay, so this is review Mohr Circle 2D. And then now we go into something that I avoided in the previous video, but I'm going to bring it up now, still Mohr Circle 2D. First, we can, for those of you that like equations, if you want to do a piece of code like MATLAB, then yeah, equations are good. We can cast the graph into equations. Because I said the principal stresses, which now I'm calling lambda, are C plus minus R. So there are really two lambdas. C is the center, plus R, it gives you sigma 1 or lambda 1, whatever. And C minus R is go there, give you sigma 2 or lambda 2. And so since we have the graph, we know what C is. C is sigma x plus sigma y divided by 2, because this is sigma x, this is sigma y. You add them up, divide by 2, you get this value, right? Then you gotta add R, but R is a square root of sigma x minus sigma y divided by 2, because it's this minus this, that length, divided by 2, this is 40 here, square, plus tau, which is this guy here, square over there, and so that equation comes from the graph. You don't have to memorize. If you understood what I'm saying, otherwise go review it, and you have this graph that you know, you can derive this equation. You don't have to remember it. And it will give you exactly the same answer. And now this equation is simpler, but it's the same as the equation in the textbook. This is the equation in the textbook, which I dislike, because I cannot remember. I don't remember the signs. I'm sure I'm going to make a mistake. Why there are all this stuff? Well, this equation and this equation are the same. If you are a little bit good at math, not much, I mean, just spend a few minutes, you can go from here to here, all right? Or from here to there, whatever you like. They are the same equation. See, it has a minus, it has a plus, and this doesn't have this thing here. So, okay, so they're the same equation. This is the equation in the book. Okay, now sigma 1 is lambda 1 and sigma 2 is lambda 2. It's just that I switch the notation on you, not because I want to confuse you, because in many textbooks, in many publications, the principal values are lambda. And so I introduced that. Okay, so now what about this equation? How did they derive this equation in the textbook? Okay, I will tell you how they derive this equation in the textbook. So we are still on Mohr circle 2D, and I'm going to tell you how the equation in the textbook is derived. And it can be derived like this. The book says, okay, if you arrange the stresses into a matrix, which really is called a tensor, but we're not going to go into why it's tensor and not matrix. That's for a graduate course. So the stress tensor, think of it as stress matrix, in 2D is 2 by 2. And you put the stresses like this, sigma x, sigma y, tau xy, and tau xy. It's the same as plane stress, okay, like a state of plane stress, where we have only these stresses. And so now you subtract a constant, lambda, multiplied by this matrix, particular matrix that has a 1, 1, 0, 0. This is called identity. Identity matrix. So you subtract, and then you take the determinant, all right? And this will give you the values of lambda, because this guy, this guy, this guy, this guy, you know. 1 and 1, of course, you know. And so the only thing you don't know is lambda. All right? So the book assumes that if you take the determinant of sigma minus lambda I for identity, and you set it equal to 0, then you can get these lambdas, and the lambdas will be these. Will be these and these, all right? We never have to do any graph, okay? So, all right, so bear with me just a minute. Now, why the book says this? Oh, there is a why behind this, but it will take me an entire video to explain other things so that you can understand why this is determinant of this will give me the lambdas. So you have to take it at face value just because I say so. If you challenge me, I can derive it, okay? I have it in the notes. So for now, let's just say, okay, let's say Dr. Barbero said that if you do this, you will get the lambdas and they will be correct. All right, so then let's move on. So now if I operate here, you see sigma x minus lambda times 1. I can put right here, sigma x minus lambda. And sigma y minus lambda times 1, I put it there. And tau xy minus lambda times 0 becomes tau xy. Tau xy minus lambda times 0 becomes tau xy. So this is the same, okay? All right, but now I put a determinant of a single 2 by 2 matrix, and everybody knows how to get the determinant, right? This times this minus this times this. So I do that. This times this, so this times this go there. Minus this square. Okay, so this equation is the same as this equation, which is the same as this equation. Okay, and the book is saying that if you do this, you'll get the lambdas. All right, so now what we can do is expand this. Now I got this minus lambda with this minus lambda becomes lambda squared. Agree? Then I got this minus lambda sigma y, and I got this minus lambda sigma x, so I can put it as minus lambda sigma x plus sigma y. And then I have minus tau xy, which I'm going to put, and then wait a minute, I forgot about this. There is sigma x and sigma y, which is positive, so I put it right there. And now I got it. Now I recognize that this equation It's a second order equation. In math, you have seen this. Here it says x, yes, but it's the same, lambda. And these guys, you know, this you know, this you know. So the only thing you don't know is lambda, but it's a second order equation. Second order equation we can write as lambda squared plus b lambda plus c, which is this nice form where this coefficient is 1. And okay, but then how do I solve this equation? Oh, we know there is an equation that this I remember because I use it so many times. Minus b over 2 plus minus b over 2 squared minus c. All right? Okay, so we have the equation for the lambda. All right, so, and how much are the b? Well, the b is whatever is in front of the lambda, so that it's gonna be minus, don't forget the minus there, sigma x plus sigma y, that's the b. And the c is all this stuff, minus tau xy plus sigma x, sigma y, all this stuff. And then you put it here. Now, here I put book equation because if you substitute this and this into the solution, which is this is a solution. Substitute the c and substitute the b in there, you get the book equation. You get this equation. So if you get the equation in the book, and we believe the book, then this method of taking the determinant of this minus this should be good because it allows me to derive the book equation. Okay? All right, so that's one way to convince you that this is good. There is a very formal way to do this, but it's more complicated. All right, so then we use our example, sigma x 80, sigma y 0, tau xy minus 50. We calculate b. B is minus sigma x plus sigma y, so this is 80, so b is minus 80. And c is all the stuff, but sigma y is 0, so it's just this, so minus 50 squared. Now the tau is minus 50, square will be 50, but there is a minus in front, so I gotta put the minus, all right? So I got it there. So now that I got b and c, put b and c in here in the solution, and that's what I do. 80 over 2, okay, b is minus 80, but the solution is minus b over 2, so minus minus becomes 80 over 2. Plus minus is there. The square root, b over 2 squared, or b is 80, doesn't matter the sign because it's going to be a square, 40 squared, and plus this 50 squared, okay? Okay? So, yes, because there is minus c, and c is minus 50 squared, so then it becomes a plus. And then I clear that up, and that becomes 40 plus minus 64. 40 plus 64 is 104. If you recall from the example before, this value is 104, and I must have it somewhere. Yeah, it is here, 104. The other one is 24, minus 24. So let's go. Okay, so I get these numbers directly. I don't have to do any graph, okay? And then the equation I program here in Scilab. Okay, if you have MATLAB, then use MATLAB because why you want to learn another software. But MATLAB costs money. So if you don't have MATLAB, Scilab is just like MATLAB. But it's free. You go to scilab.org and you download it, you install it, and you get used to the interface. It takes you 5 minutes, and then that's it. You have free MATLAB. There are two main differences. There are other differences, but the main difference you need, if you want to use this, is that this is a comment. In Scilab, you put percentage. Here, you put // And second, if you want Scilab to behave like MATLAB, basically to print the way intermediate results the way MATLAB does, then you gotta type mod 0. This is a well-kept secret that I know and I'm sharing with you. So it's for formatting. So with these recommendations, then it's like you have free MATLAB. So here I put b minus 80, c minus 2500. All right, see from here, like that. And then I put the equation, this equation, minus b over 2 plus minus, well, 1 I put plus, square root b over 2 square minus c. So I like to do it this way because then if I have another problem, I can change these numbers and I don't have to mess with the equation. The equation, once it's good, is good. I don't touch it. This is my data. So I change the data, the equation will do the job. And you see now, since I put the mod 0, if you don't put anything here, or you could put a comma, but not semicolon, then it will print 104. If you put semicolon, it won't print anything on the console. So it behaves like MATLAB. And so lambda with a minus sign gives minus 25. This is nothing because you could do this with a calculator, right? All right, but I have a reason why I want to introduce this for you. Okay, so then now we go to still Mohr circle 2D, but with 3D matrix equations. Why? Because I'm trying to go to 3D. So I'm going slow to 3D. So right now I have matrix equations, and it says, oh, you can do this minus lambda times this, determinant, and you get equal to 0. All right? Okay, well, I have another way. I could do this, which now is a 3D state of stress. Okay? Minus lambda 1, 1, 1. In 3D, this matrix is going to be 3 by 3. That's the only difference. And this matrix will have the 2 by 2 matrix from before, plus this stuff here, because now it's 3D. And I could try to go further the same way we did before. That is, operate here to get this matrix. And now take the determinant of this. The determinant of 3 by 3 matrix is doable, right? There is the cofactors. And I could do it, but I'm not going to do it because 1, 2, 3, there are 3 lambdas, going to end up with a third order equation. You know, there is a formula, long formula, for third order equation. So we could use a formula, but it's going to be a very long program. And it will work for 3 by 3. But it's better to do this way. Use your software. Since we're going to use Scilab or MATLAB, just use the software to calculate the eigenvalues. What are the eigenvalues? The principal stresses. And the eigenvectors, what are the eigenvectors? The eigenvectors are the directions of the stress element. Okay, this stress element is a different direction from this. The eigenvector will tell us how to rotate this. So the software, MATLAB, Scilab, you name it, is never going to give us an angle. It's going to give us eigenvectors, and I will show you what to do with them. Okay, so we go back here, and we say, okay, calculate the eigenvalues and eigenvectors of this system, all right? Okay, all right, let's try to do that. For our example, we have sigma x 80, sigma y 0, tau x y minus 50, and these 3 are 0. So we put these numbers, and you see, even I casted the problem as 3D, but really it's not 3D because this is all 0 and this is all 0. So what I have is this 2 by 2 minus lambda and this 2 by 2. This doesn't matter because it's all 0 minus this 1. Okay, but I can move forward, all right? And so now I got the same. Here I repeated from previous slide. And I write it in this formal way where I put sigma in bracket, that means this whole matrix, minus lambda times I in bracket, that means that I is that matrix over there. Just a compact notation. Sigma is the 3 by 3 matrix of stress, and I is the 3 by 3 identity matrix. And now what are we going to do now? Now we're going to use the software. The function spec in Scilab, which is named Eig in MATLAB, they do the same, can be used to solve this problem, all right? So then we don't go directly look at the code. Well, first there is this comment, the mod 0. Now I put all my data into variables. This is, is because I like it this way. And then the formula is not contaminated by numbers where I can make mistakes. The formula is this, and if this formula is good, it's good forever. I can put whatever data I want right here. Okay, so I put sigma x, sigma y, sigma z, which is 0, sigma z, yes, 0. Tau x y minus 50, 0, 0. Okay, now the formula for sigma is this, x, xy, xz, xy, y, yz, xz, yz, z. And so it's going to copy these numbers here into a 3 by 3 matrix. And this is the statement for spec. Now, here I put do not print because I put this semicolon, so it won't print. Otherwise, it was going to print this and it's going to print that. These are the principal stresses, eigenvalues, and these are the directions, eigenvectors. And since it didn't print, then I got to type lambda without a semicolon, and then it's going to give me the values in the console, not here in the program, but in the console. And if you know MATLAB, you know what I'm talking about, right? You don't put a semicolon, you're going to get numbers, right? Okay, So I got the same numbers, all right? And if you don't trust me, okay, type this code in MATLAB or Scilab and you'll see. Okay, so now, okay, here I show you the console. This is the console of Scilab. And since I put in the previous slide semicolon here, and when I run this code, it doesn't show me anything, all right? So in the console, same as MATLAB, I can go there and I put this comment, see, // eigenvalue lambda. I type this for you to see. Then I type lambda with no semicolon, and then boom, it's giving me this. So these are the lambda. Okay, where are the lambda? Oh, the minus 24 is there. Then there is a 0 here, and there is 104. 104, I remember. This is the largest. Yes? And then there is one that is 0 because this is a 2 by 2 problem. It's a 2D problem. And so, and then the minus 24. Oh, okay, it's giving me the right lambdas. Correct? You agree? Okay, but the first problem I see is that they are not ordered, and we definitely need them ordered. For the rest of the semester, for design, we need them ordered. We need to know which one is the one, lambda 1, and lambda 2 and lambda 3. So this has to be minus 24, and this has to be 104. No software will order them for you. You have to do it yourself. Okay, maybe you can write some code to reorder them. But when they come out of the software, they will come up like this, all mixed up. Okay, it will be just a big coincidence that you will get them ordered. So, but we look at the numbers and we say, yeah, this is the largest, so this must be 1, although it's in position 3. The smallest must be 3, although it's in position 1. And the intermediate, which is this 0 here, must be the 2. That's the only one that is in the right position, in 2. Okay? All right, so then I type this comment eigenvectors v for you to see. Then I type v. When I hit enter, I get this. Now, the first thing you need to learn is that for each eigenvalue, each principal stress, 104 say, this column is the eigenvector. Okay? And of course, for this column, which is this value, is the eigenvector. The fact that this one is in position 3, that means that is pointing in the z direction. That means coming out of the screen right here in the middle of this square. All right, so the eigenvalue, the stress is 0, yes, because sigma z is 0. And in which direction? Coming out of the screen, because that's the direction z. Now this 104, it has these directions. What do I do with these directions? Well, I see what vectors I can build with these directions. All right, and the only vector I can build with this direction of these 4 vectors is this, because in this I can go minus 0.9, this is minus 0.9, I go minus 0.9 there, and then positive 0.43. No other place I can do that, all right? So this must be, guess what, lambda 1. Why 1? Because this corresponds to the 104, all right? Now, if you want the angle, like we did with Morse circle, well, it's easy. You got this number, use the tangent, you get the angle, correct? By the way, the angle is not at scale here because my sketching software doesn't give me much flexibility, but you know what I'm saying, right? You use this and tangent, you can get this angle, and then that angle will be the theta p. Now, when we did Morse circle, we didn't put all that stuff here, we put it over here, right? But the computer has no way of giving you the numbers down here. It will give you whatever numbers the computer wants. Because it's irrelevant, the sign is irrelevant, and so it's going to give you something. And you have to be smart enough to realize that the computer is talking about this, all right? And for that, I'm going to go back. We're here, you see? Always we say, oh, sigma 1 is this, and we put it there, and we say this, and this is the angle. But this red is the same as this black, right? The value is the same. So if I give you this direction, well, okay, you know this direction, okay? It's the same direction with a minus 1. Okay, so now we got this one. This is 0, and then the direction is perpendicular to the screen. And then what about the minus 24? The minus 24, it's in such direction that I have to use these 2 negative numbers. All right, where I can use 2 negative numbers? The only one that has 2 negative numbers is this, because this one has a positive, this one has a positive, so I cannot use that. So I gotta go in the direction x. because this row is x, right? This is y and this is z. So in the direction x, I go minus 0.43 there. And then I go down in the direction y, 0.9. And this is lambda. And what is lambda? 3. Why 3? Because this is the smallest. And according to the order, it is like this. Okay, so there is a lot to learn in this slide and a lot to remember. Okay, so then let's see what we got now. Now we have, from previous slide, we have the 2D Morse circle by software done. Okay, done, perfect. Yes, we can do, why do I say we have everything done? Because if the computer tells me the values and I order them, I say 1, 2, 3, because that's the largest, this is the smallest, this is in the middle. And I know what these numbers mean, so I can get the directions. And if I have the direction, I can get the angles. Then it's like doing Morse circle. I got everything. And all I have to do is I have to write this little piece of code, which is this statement, really. Yes, only that. Okay. So now I can do the same for 3D. So if a 3x3 matrix is fully populated, then we do the same. And for fully populated, what I did is I took the 2x2 example and I put another 120. Okay, this is a little bit of a trick because you see I'm not putting numbers there. I can put numbers there, but the orientation will be not so clear. So I put this number there, and if I put this number there and these are zeros and these are zeros, I already know that this is a principal value. Now here there are no principal values showing because I don't see the 104 and minus 24, right? They are hiding. I have to rotate, transform the coordinates to find them. But this one, since it has 0, 0, 0, 0, I know that is already a principal value. But it's a valid example, okay? It has sigma x and sigma z different from 0, sigma y 0, and tau is y negative. It's a valid example. And if I do this, and I calculate the eigenvalue and eigenvector, then I should get everything. All right, so the code is the same code. The only difference is this. I put a 120 there. All right, so I put a 120 there. This code that didn't change, this didn't change. Now, of course, the numbers now are going to be minus 104, minus 24, and 120. You see, we get another number, and it's the principal value, okay? And it's the principal value because there are no shear in that plane, the XZ plane. Right? Yes. So, okay, so then, so we look at the console, all right? The console says, oops, 120 now is here, 104 in minus 24, all right? Oh, okay, so it looks like it's ordering them in some way, and it's putting the largest at the end, but we need it at the beginning. And the 104, it's in the middle, and this is the most negative, that's the smallest. Okay, and the V's, what do we do with the V's? Well, the 120, which is the largest, points in the direction Z. Okay? And so that means, but this is the direction 1, because it's the largest. 120 is lambda 1, so for us it's going to be the largest. So it's going to be this. Okay, so then what about the 104? The 104 is the one that has minus 0.9.43, minus 0.943, but now it's lambda 2. Okay, now, before it was something else, right? It was lambda 1. Now it's lambda 2. Why? Because it's the second one. It's not the largest. The largest is this. And, okay, and the minus 24, which remains lambda 3 because it's the smallest. Is this, the one that has minus 43 minus 0.9, minus 43 minus 0.9, so it must be this. So I got everything. I got the values, and I got the directions. And from the direction, I can get the angles. Okay? All right, and so now we can draw the Morse circle. So you see, for Morse circle 3D, you cannot draw the Morse circle like we did for 2D. You have to get the values first, then you draw the circle. And we get the values from using the software. All right, so once we got the software, then how do we draw these? Well, we put a little mark here for sigma 1, which we know how much is it. How much is it? It's 120, okay? And then for 2, we put 104. And for this, we put minus 24. It's not to scale, all right? It's just a sketch. So once you have this number and this number and this number, okay, what do we know about Mohr circle? We know because Mr. Mohr said that all the possible state of stress have to be on the circle. They cannot be inside, they cannot be outside. They have to be on the circle. So what circle? Well, between 1 and 2, like when we did Mohr circle 2D, there was only 1 and 2, right? So between 1 and 2, we can draw a circle, and it is circle. Yes? And this value is what we used to call tau max, but now you can see that this is not tau max. Tau max is that. And this is very important, and maybe the only reason why I'm doing all this video. So you understand that there is a tau that is larger than this. And before, we were convinced that this was tau max. In fact, we call it tau max, but now forget it. It's not tau max. Tau max is this. So in between 1 and 2, which one we know because we calculated with software, we can mark here the axis, mark here the axis. We gotta do a circle because Mr. Mohr says that all the state of stress are on the circle, right? So we do it. Now between 2 and 3, we make this little Mohr circle like that, which has its own little tau, but is irrelevant because this is the largest. And between 1 and 3, that means between the maximum principal stress and the minimum, that will be 120 and minus 24, we do another circle. And now once we have these 3 circles, then we decide, yeah, this is tau max. Tau 1, 3 is tau max. So we cannot draw the Mohr circle until we calculate the 3 principal stresses, and we do that with software. We have to order them so that the largest is 1, 2, and 3. And that is because later there are equations that are derived in chapter 5. There are equations that assume that these numbers are ordered. Notice that tau max is tau 1, 3, which can be calculated easily as this minus this divided by 2, and not tau 1, 2 or tau 1, 2, 3, okay? So that means that we need all 3 principal stress values to calculate tau max. We gotta know this, this, and this to decide which one is the smallest, which one is the largest, and then we can calculate this. Okay, so as a summary, well, same thing. We cannot draw the Mohr circle until we calculate all 3. We must order. We need the 3 principal values to calculate tau. And what is the big deal about tau? Why tau max? Well, because it controls yield, plasticity, and the yield safety factor, which is the most important thing for metal design. So we gotta know about tau max. It's very important. Now, as a corollary, the eigenvectors can be used to predict the direction of failure. We shall see in chapter 5. Sometimes it's interesting or needed to know which will be the direction of failure. If it fails, in which direction it will fail. And the eigenvectors, which are these little vectors from which we can get the angle, will help us with that. Okay, so with that, thank you very much. That's all for today.